Hi everyone, my name is Ashika and I'm learning ROS2 with Python, and these are my first steps. My motivation is to master ROS2 in depth and understand how it works from the inside. And my final goal is to build an autonomous navigation program from scratch by incorporating everything I learn. I am using the MentorPy robot with Raspberry Pi, and I'm using that via a VNC viewer. Okay, so now we're gonna go top to bottom through this open loop code, and the whole point of the script is to move the robot 2 feet forward, using no sensors and no inputs, just based off of time. We're gonna move the robot 2 feet using this script, and this is an open loop script, so it gets no feedback. So here we can see the robot move with this exact program. The back wheel should be aligned with the middle of the tape for the front and the back, and we see that it missed the mark a little bit since this is an open loop code. It's just a harmless leftover. And then import time, it just gives us the time to measure in seconds for our open loop timing. And then import RCLPy. So RCLPy is a Python client library for ROS2, and it's what lets a normal Python script talk to the ROS2 system. And then here, node is a base class that every ROS2 node inherits from. And then twist is the message type that we publish to move the robot, which consists of angular and linear velocity. So here, when we start from the class and constructor, so here we're defining a class move distance that inherits from node. And inside initialize, the very first thing we do is call super initialize, and this registers our node with ROS2 under the name move distance node. And every ROS2 node needs a unique name, and this line is where that happens. And then we're declaring parameters here in these 3 lines. All of these 3 parameters, each with a default value. So distance m, this defaults to 0.6096 meters, and that's exactly 2 feet in meters. And then linear speed defaults to 0.15 meters per second. And then here, command velocity topic, this defaults to controller command velocity. Then this is the publisher that will send commands on. And because these are declared as parameters rather than hard-coded constants, you can override any of them from the command line at launch time without touching this file. And then here we're just reading the parameters into instance variables, and here is where we pull each parameter's actual value back out and store it. Linear speed is wrapped in absolute value, which protects against someone accidentally passing a negative speed, which would otherwise make the robot drive backwards when we expect forwards. Okay, and then here we're validating the speed. So if the speed is 0 or somehow still negative, we log an error and raise system exit 1 to stop the program immediately. This matters because our very next line divides by this number. So if the number was 0, the program would crash with a much less helpful error message. So this check fails fast with a clear one instead. So here is creating the publisher, and this line creates the publisher object. We tell it the message type, which is twist, the topic name, which is just whatever was passed in as command velocity topic, and a queue size of 10, which is how many outgoing messages ROS2 will buffer if something downstream is briefly slow to receive them. And then over here is where we're calculating the duration of the drive. So this is the most important line in the whole script. There's no position feedback here, and we're not measuring how far the robot has actually traveled. We're just doing time equals distance divided by speed. So we want to go 0.6096 meters at 0.15 meters per second. And whatever that number comes out to, the robot will drive forward for exactly that long and then stop, regardless of whether it actually covered the full distance in the real world, which this is what makes it an open loop. And then here we're just logging what we're gonna do, and this is just to print a status, like for example, it will drive forward for this many meters at this speed. So here is the timer rate, and we're picking a control rate of 20 hertz, which is 20 times per second, and then converting that to a period in seconds, which works out to 0.05. And start time is initialized to none, and then we fill it in the first time the timer fires, and then create timer is what actually starts the loop. So every 0.05 seconds, ROS2 will call self-timer callback. And then here is our control loop, and in each tick we grab the current time. The first time this runs, start time is still none, so we record now as our starting point, and each tick after that elapsed here tells us how many seconds have passed since the robot started moving. And then this line here is where we build a fresh twist message each tick, and if we haven't reached our target duration, we set linear.x to our driving speed and angular z to 0. So over here, once elapsed time reaches or passes move duration, we fall into this else branch, and this is where we zero out both linear and angular velocity and publish that stop command. And then we're just logging a message here, and then we call the self-timer.cancel. So this stops the 20 hertz loop from firing again since we're done driving. And then this last line here, this schedules one more timer, which is 300 milliseconds out, that calls shutdown. And that short delay matters, and it gives ROS2 time to actually flush out that final stop message over the network to the motor controller before the node disappears. And if we shut down instantly, there's a real risk the stop command never makes it out and the robot keeps going. And here is just a shutdown helper. So this is a small dedicated method whose only job is to call rclpi.shutdown, which tells the whole ROS2 system that this process is done. And keeping it as its own method is what lets us schedule it with a delay using create timer as we just saw. And then walking through this last block here, this is the main argument. So here, initialize, it starts up the ROS2 system for this process, and this has to happen before any node is created. Node equals move distance is what constructs our node, which runs everything we just covered in initialize. And this is what actually keeps the program alive and processing. It sits in a loop and it waits for timers to fire and callbacks to run until something stops it. So over here, try is where the loop starts, or spin is where the loop is starting, and except for keyboard interrupt. This is Control C. When you do Control C on the terminal, it stops the program. And then finally, this is just a failsafe in case there's an error and the program crashes and doesn't shut down. We just stop the robot from moving, and this is where we call the linear and angular velocity to be 0. And finally here, this is where the program is just making sure that you can only run this script when it's executed directly instead of if it's imported to somewhere else. And stepping back, we notice that nowhere in the script do we ever actually check the robot's position, and we never ask how far have I really gone. We just compute distance divided by speed, and once a timer runs for that many seconds, and we trust it. So that's the definition of an open loop control, which is simple and predictable, but there's no way to correct for wheel slip, a low battery, or an uneven floor. And if the real robot is even 10% slower than the linear speed parameter assumes, then it'll fall short of the target distance every time. And the fix for that is a closed loop control using something like wheel encoders to measure actual distance traveled, and we're going to go over that script in this video. So here we can see the closed loop program. We can really see how it works from here. So this is the topic that we have, the controller command velocity, and then this is our message type that we're sending to this subscriber. So this is going to be the publisher of the controller command velocity, and our controller node is subscribed to that. And it's in a loop because our controller node gives us the odometry information, which the node of the program gets, and it decides what to do with that information and sends it back to our controller. So here is the closed loop program, which does the exact same thing. The robot moves 2 feet, and closed loop means the robot actually checks its position as it drives using wheel odometry and stops when it's actually traveled far enough, not when a timer says it should have, and that's the whole philosophy behind the script. So let's build this up. Before that, we can see the robot in action and see that it hit the 2 feet mark precisely with the encoders. Okay, so starting up here, we already went over these imports, but I want to draw your attention to QoS profile. So QoS, or quality of service, this controls how many messages are sent between different nodes. So imagine sending text messages. So do you want every message guaranteed to arrive, or is it okay if you occasionally miss one? So different applications have different needs, and QoS lets us choose which one you need. And finally, there's 2 message import types. So there's one for twist, and then there's one for odometry. And this line here, this is basically a toolbox which twist is from, and same with navigation. And then here again we see that this is the class that we're creating, which inherits from node. That means it automatically gains all of the tools ROS2 provides, like publishers, subscribers, timers, parameters. And again here, this line, this registers a program with ROS2 and gives it the name move distance closed loop node. And once this line runs, that means ROS2 knows that this code exists and other nodes can communicate with it. So here are we're just declaring parameters again, and there's more this time. There's the odometry topic, and then there's distance tolerance. There's a control loop frequency here, and then a timeout in case something goes wrong. And then again, drawing back to this, the good thing about parameters is that we can change them without editing the code. So for example, if we wanted the robot to drive 1 meter instead of 2 feet, we can override the parameter from the command line. And then the next block here, so after declaring the parameters, we have to read their values again, so that's where we're getting the actual values. So these lines simply copy the parameter values into variables, which we'll use throughout the program. And again, both distance and speed are wrapped in absolute value, which means that if someone entered a negative number, it still uses a positive value instead. So finally, we check whether these settings make sense. So a speed of 0 or a negative distance would never let the robot reach its goal. So instead of continuing with these false values or bad values, the program immediately prints an error and exits. And this is just to validate our variables and make sure nothing goes wrong later on. And here comes the variables that store information while the robot is running. And these are the state variables because they describe the current state of the robot. So start X and start Y will remember where the robot began, and they're set to none because we don't know the starting position until the first odometry message arrives. And then current distance keeps track of how far we've traveled. Odom received false. This tells us whether we've received any odometry yet. goal reached remembers whether we finished, and then elapsed underscore s for seconds acts like a stopwatch for our timeout. And then here is how we connect our node to the rest of ROS2. So the publisher is sending velocity commands, and every time we publish a twist message, the robot receives a new speed command. And the subscriber does the opposite. So instead of sending information, it listens for the odometry messages. And whenever a new odometry message arrives, ROS2 automatically calls our odometry callback function, and it does it for you every time new information arrives. So here is the QoS profile, and we're using best effort reliability. So that means if one odometry message gets lost, we don't have to worry about it, and that odometry updates arrive many times every second, so another one is already on the way. We also tell ROS2 to keep only the most recent 10 messages with this depth of 10. Since we're only interested in where the robot is right now, there's no reason to keep older data. And you have to make sure that your publisher and subscriber have matching reliability or matching quality of service, which are compatible. So when we scroll down here, this is one of the most important functions in the program. So every time the robot publishes new odometry, ROS2 runs this function automatically. First, we read the robot's current X and Y position, and the first time this callback runs, we don't calculate any distance. Instead, we save the current position as the starting point. From then on, every new odometry message compares the robot's current position to that starting position. And we calculate dx, which is how far we've moved in the x direction, and dy, which is how far we moved in the y direction. And we use a Pythagorean theorem over here to find the straight line distance. And this is where we're using that math import. And this gives us the robot's displacement from where it started in case of any wheel slips. And moving on, here is the control loop, and this is where the robot decides what to do. So this function runs 20 times every second because we set our value up here. We set it to 20 hertz initially. Here, control rate, we set that to 20. So it's going to run 20 times every second. So first it checks if we've received any odometry yet, and if not, there's no way to know where the robot is, so we simply just wait, and then we calculate how much farther we need to travel using this remaining variable, and then we create a new twist message, and this brand new twist starts every value equal to 0, and that means unless we set a speed ourselves, the robot won't move. So if the remaining distance is smaller than our tolerance, we're done, and we set both the forward speed and turning speed to 0, and then we publish that stop command. And after we cancel the timer so this control loop stops running, finally we wait a short moment before shutting everything down, and this tiny delay gives the stop command line time to reach the robot. Over here it's 300 milliseconds. So the next check here is timeout. So if we've been driving longer than 30 seconds, the program can tell that something probably isn't working correctly. So for example, maybe the wheels are stuck or odometry stopped updating. So instead of driving forever, we have to stop safely and exit, which is the same logic as this check over here. So over here, if we haven't reached the goal yet, we keep driving, and most of the time the robot drives at full speed. However, once it's within 10 centimeters of the goal, we gradually slow it down. And this helps reduce overshooting and makes the stop much smoother. And also because the control rate is 20 times per second, it reduces the error if you slow the speed down. And then here is the main function. Here is where the node is initialized and it spins, which is basically an infinite loop. we already went over this except keyboard interrupt, which is basically if you press Control C on your terminal to stop the program before it's finished. And then this is just a final safety check. And then before exiting, we publish one final stop command to absolutely make sure that the robot still isn't moving in case our other fail-safes didn't work. And if for some reason the publisher isn't working and stop twist isn't working, it's just going to just destroy the nodes, so the program stops running anyways. Again, one final look, we see that the closed loop program with the odometry feedback is much more precise compared to the one with just an open loop and no feedback.